This is the results of the simulation contest. So let me just go through this thing. Okay, so we'll just hang it out. No, I like the simulation contest. I hate the thing that sits on top of my screen, so I can't read anything. Okay, so this year we had a lot of entries sort of at the last minute. And like last year, we had a hard time choosing winners because there's a lot of really cool visualization. So a lot of these we're hoping to get permission from you folks to show them on the MFM webpage. Without further ado, I'll go ahead and present this. You guys get to look at one of my favorite astrophotography pictures that I've taken, because that's one of my hobbies, and I'm presenting this, so I get to force this on you guys. So we held the contest. It's for the most interesting simulations and visualizations. We kind of have a couple different approaches to judging it. We're looking for like the aesthetic look, sort of novelty of the approaches. So like if you're solving some really cool equations or something like that, and the notability of the application. We hope to put the results on the MFM webpage. The winners of the two categories will be receiving MFM t-shirts in the mail. So you'll talk to Zanio about that. Yeah, he's demoing the shirt. Okay, so we've got two categories. We've got still images and animations. So the runner-up for still images was Matthias Schmidt over at here at Lawrence Livermore. He's got a flow through a periodic gyroid microcell, and he's solving the flow with the Navier mini app with this additional Brinkman penalization. So this is one of the coolest applications of periodicity using MFM that I've seen.
Is Matthias here?
Yeah, are you here, Matthias? You want to say a couple words about this? Maybe he's gone. Maybe he's gone. We'll catch him later. Congratulations, Matthias, if you can hear. Okay, and the winner for still images is, drum roll, Ben Zwick from the University of Western Australia. We saw this earlier in one of the talks. So these are streamlines of the electric field generated by a current dipole source located in the temporal lobe of an epilepsy patient. The finite element solution using a regular hexahedral grid was implemented at MFM, and visualization was in ParaView. Ben, are you still here? Any chance?
I think it's like 4 a.m.
I think he's in Australia. He might have stayed up to find out he won, but we'll send him a t-shirt and contact him. I'd love to pick his brain about how he did this work. Yeah, let's talk to him. Yeah. Okay, and we've got the runner-up for animations. It was Tim Brewer from Synthetic Applied Technologies. Let me go ahead and play on this so you can see it. You saw some of this in the talk before. So this is single phase compressible Euler simulation using DG discretization to describe supersonic, it's a Mach 2.5 flow around cylindrical obstructions. The simulation leverages Synthetic's newly developed code for highly compressible flows. Tim, are you still on the line?
I'm here. Yeah, that's great. No, thank you so much. That's really cool. Yeah, I mean, I think the description does it all. I think big shout out goes up to Kitware and ParaView for giving us the tools to make these happen. But no, really happy, and thank you for selecting me to be runner-up.
Excellent, thanks, Tim. Oh, I'm gonna go forward. Okay, and the winner for animations, drum roll, please. It was a split decision. We couldn't decide. So winner number one was Tobias Duswald, who's worked with some of our team members. So this animation presents a topology optimized heat sink obtained with a new algorithm developed by a team here at Lawrence Livermore. The objective is to minimize the thermal energy in a domain with constant internal heating. In this problem, there's only one exit point for the heat to escape, namely at the central region of the upper boundary, and the amount of material in the heat sink is constrained. witness that the solution appears almost organic. This is one of the coolest things I find about topology optimization. You get really organic looking solutions. So Tobias, are you online?
Yes, I am.
You
Give me
say a little
second.
more about this and how you made it?
Yeah, well, actually, this was also a lot of work from Brandon and from Socrates. But yeah, we really like this font because, as you said, it looks super organic. Sorry, I'm a bit out of breath in the gym right now. But yeah, it was just like a very interesting work, and especially the visualization looks super cool. So thank you for selecting that.
All right, congratulations.
Congratulations.
Thank you, appreciate it.
Let this play one more time there.
You have to send me your t-shirt size and address.
Yeah, for sure. Okay, and finally, the other winner for animations, was Will Pasner from Portland State. Let me go ahead and play this while I describe it. So this is a magnetic diffusion problem, solved to compute the magnetic field induced by current running through copper wire and air. Problem solved using solved using the A5 formulation using GPU accelerated low order refined solvers in H1 and H curl. Magnetic field is represented in an RT finite element vector field in HDiv. Will, are you still online?
Yes, I'm here. Thanks very much. Yeah, this was a great contest. The other entries were also amazing.
All right, congratulations, Will.
Thank you. And what else can I say? MFM makes it easy.
There you go. There you go. Well, thanks, Will. So I think I'm just going to go ahead and close out here. Oh, wait, no. I can't forget the honorable mention.
There is a special category.
We had to invent a special category for this visualization because it was so interesting. Julian, who's sitting next to me, put together turbulent, incompressible Navier-Stokes LES flow through a periodic hill. However, he really with a twist. So I'm going to see if I can go ahead. And I got to stop share and then reshare to get the right screen because I can't play this one again.
Let's see how this will.
Let's see if I can get it to come through. Yeah. There's that. Share. And then I got to make sure I'm sharing sound because I need the sound. Oh, where is it? Yeah. Does it know when you go to share? Share sound. There it is. Okay, let's see how it goes. We'll find out.
You don't get the.
So I hope that came through. That's so I don't know, I don't know whether I'm at a finite element conference or a rave, but all I know is I like it. Oh. All right, so I'm going to go ahead. I've got just a few closeout slides that I wanted to show you guys. So I'll go ahead and share those. Did everyone see that?
Yes.
Excellent, excellent. We'll have that on the website too. If
We have to check with you as a nice.
yeah, good call. It'll be our new intro to the website, right? Okay, so I got a few wrap-up slides, so I'll go ahead and present these real quick. So I just wanted to throw up some MFM resources for those of you who are still kind of getting started. We've mentioned these before, but I'll mention them again. So we've got the MFM repo, of course, on GitHub. And if you back out sort of one step from the MFEM repo, you get the MFEM organization, where you can find the MFEM group. And if you want to join there, it's a good way to, it's kind of a mailing list for us. If you're having trouble, hit us up on the GitHub issues as well. We've also got the mfem.org webpage that's constantly growing. More and more information there. You can find the workshop page there as well. You can also find our seminar series page there. So if you're interested in seeing our seminars or delivering a seminar, go ahead and look that up as well. On the mfem.org webpage, we've got our publications. This publication here that I've listed is sort of our canonical, oh, I'm using MFEM and I want to reference you guys, use that one. Unless you're, working specifically on an algorithm with us or something like that, then we might have another. Please feel free to keep contacting us on the workshop Slack. And again, long-term, so we'll solve issues for you today and maybe for the next few days on the workshop Slack. And then sort of longer term, when you run into problems, go ahead and contact us on issues. We're pretty on top of those. So you should be able to get a hold of us there. I want to give gratitude and applause for the speakers. So I'll actually just give a round of applause for the speakers. I want to give some special thanks to the planning committee, Zanio, Will, Socrates. I've missed Caton in there. I'm sorry, Caton. And Holly for everything she's done to help make this go. And thank you all for attending. So I'll just go ahead and close out with a thank you from the MFM team. This picture on the left here was recently taken at our Lawrence Livermore 70th anniversary. So some of the core team was here to attend that. So we snapped a good picture. But on the right, we actually have all of the contributors on GitHub. And thank you for all the work you've done on MFEM as well. We're better code for it, and we're happy to have all of your contributions.